Okay, for the second video of this revision, we're going to be looking at the CPU particularly. For the CPU, you need to know three things: the components of the CPU, the key things that affect its performance, or how fast, how well it can manage the system, and also looking briefly the FDE cycle. You do need to know some parts of the FDE cycle, but you don't need to know it in detail. Okay, so I'll make it very clear what you do need to know. So as we know, we have the layout of the computer. So we talked about storage devices already. The CPU is the device that is going to be synchronizing all the other parts of your computer. So that basically means sending signals to everything to let it know what to do and to take the information in as it comes in. It's obviously running the instructions of your algorithms as well, which is its kind of primary purpose. So everything connects to CPU because it is going to be controlling everything, and that's an important thing to remember. And the connection, how we connect to the CPU, is through something called a bus. Okay, so the bus will connect devices from devices to the CPU. So these little arrows here are all buses. Just a little side point. I'm sure you've heard of USBs before. USB stands for Universal Serial Bus. The word bus comes up again because it's connected, shock horror, to the CPU using a bus. Okay, so remember your CPUs run instructions. Instructions are stored in binary. Okay, so they're not stored as if A equals B or things like that in Python. They're not stored like that. They are stored in binary, in machine code. So we don't understand machine code. I don't understand machine code. I can't read it. Okay, but the CPU can. So it's machine readable, not human readable. So in order for instruction to run, we have to take it from RAM and fetch it into the CPU. Okay, that's why we call it the FDE cycle, the fetch, decode, execute cycle, because the first thing you have to do is get the thing from RAM into CPU. Okay, and there's a little animation for you. So CPU components, there are three main parts you need to be aware of: the ALU, the CU, and registers. Let's dive straight into those. Registers are really important. These are temporary values which are stored inside the CPU. So they're like little blocks of memory. These are really fast. They run at the same speed as the CPU, okay? And they're used to store values as a program is running. So rather than having to copy it back to RAM again, or even to storage devices, values are stored in registers initially, just while it's working it out, and then once it's finished doing its calculations, that's when we can maybe start storing stuff into RAM and storage devices, etc. There are two types of registers. There are general purpose ones, which we use just to do calculations and store stuff temporarily, and then there's special purpose ones which you need to be aware of. The special purpose ones you need to know about are listed on this slide. You've got the prem counter, the MAR, the MDR, and ACC, and we'll delve into what those ones are now. So the next one I'm going to look at is the arithmetic logic unit. The word arithmetic means maths, basically. So adding, subtracting, dividing, that kind of thing. So that's what we refer to as arithmetic. And it also deals with logic. So logic is things like our and, or, and not. So remember, anything where we end up with true and false values. Okay, so thinking back to our Boolean algebra days. Whenever we do a calculation or a logical operation, we'll always store the answer, the result, into the accumulator, okay, the ACC. So that register stores basically the result of everything. The last one is the control unit. So the control unit is really important because it has the job of actually executing, running ARM instructions. Okay, it's got that big important job. It will decode the instruction first, because remember, this is going to be just a bunch of ones and zeros in binary. The CPU does need to work out, well, what instruction does that binary mean? Okay, so it needs to have that little kind of calculate, that kind of workout. It's not really calculation. So it looks at the binary and works out what instruction it needs to do. It controls the CPU timing, okay, so it sends a regular pulse. So remember, we measure the speed of the CPU in hertz, and that's how many times you can do something per second. And it's just got this regular pulse, so like this, just kind of obviously a lot faster than that. And every time we have a pulse, it's finished an instruction, okay? That's what we mean by that. And also sends and receives control signals, so it has the job of controlling the other part. So we'll send a signal to RAM, for example, what, send me some data, please. Or send the instruction to storage, say, save this data, please. Okay, so it will send signals to the other parts of the computer to tell it what to do. So the last thing we need to be aware of is the FD cycle, or the next thing, should I say. The FD cycle is really simple. You don't need to know this in massive detail. You need to know that it fetches. That means getting stuff from RAM into CPU so we can actually run it. Decoding, that means, well, I've got a bunch of ones and zeros. What on earth does that mean? Oh, I know. I've decoded it, works out what it is, which instruction it means. Okay, so it has that job of determining what instruction has just been fetched, ready to be executed, where it actually does the job. It actually runs the instruction. So we fetch it from RAM, work out what instruction we need to do by decoding it, and then finally running it. Okay, instructions, ladies and gentlemen. Okay, so when we talk about instructions, we are talking about the kind of commands inside our programs. Now, we will have a program which might be loaded up into RAM, and we need to, one at a time, copy those instructions into CPU. So we've already kind of covered that already, but each instruction has an address where it can be found in RAM. Okay, it's known as a memory address. Technically, it is just an integer number. Okay, these numbers can get quite big, but ultimately it's just a number, and it works a bit like an array. You know, you've got an index in your array. You've got the first item is 0, then the next one's 1 and 2. You get the idea. Memory addresses are very similar to that. Okay, so it's just a number saying, well, okay, which memory location can I find an instruction or a bit of data? So that's a memory address. So we have some key registers you need to be aware of. We have the program counter, and that stores the address, so where can I find it in RAM, of the next instruction that I need to fetch in. Okay, so we're always pointing to the next thing we need. Okay, so I fetch one in, oh, I'm pointing to the next one I need. Okay, fetch that one in, I'm going to point to the next one. So it's almost like, imagine you're in a queue, and the first instruction that's being fetched is the first person in the queue, and then I'm the program counter, I'm pointing at the next person, the second person in the queue. Then the first person goes off, that second person is now being fetched, it's walking to, I don't know, the till, and I'm pointing to the third person. Okay, then the third person comes along, I point to the fourth person. So I'm always pointing to the next instruction, that's the program counter. The MAI and MDR work together, so as I am fetching instruction, so maybe bringing the front person to the till, for example, that is the address of that instruction being fetched. Okay, so that's pointed to the instruction I'm fetching, and once it's been fetched, it will end up in the MDR or the memory data register, which stores the result of fetch. So program counter is always pointed to the next thing I'm fetching. The MAR is pointed to the one I'm currently fetching, and finally the MDR is the result of the fetch. Okay, so when the instruction has been fetched, that's when it ends up. Okay, that's the instructions. So now looking at performance of the CPU. These are ways we can improve how fast our system runs. The first one is cores. Normally, a CPU can only run one instruction at once. However, I might have more than one core. That means I can run more than one instruction at once. Okay, so having 2 cores allows me to run 2 instructions at once. Having 3 cores, 3, and so on and so forth. So each core is capable of running one instruction at the same time. So that's really useful because it means I can do more than one thing at once. However, it doesn't mean that one program is going to get twice as fast, okay? Because some programs have to be run one after another. So there's no point me trying to do the same thing. So give you an example. Imagine I was washing clothes, okay? I can't wash them and dry them at the same time. That makes no sense. Okay, I can't do that. But I could have one load being washed and another one being dried. Okay, two separate loads would work, but I can't make the one load of wash and dry at the same time because it just doesn't make sense. Okay, so the same happens with programs. We can't run the first instruction and the second one at the same time because they run in order, don't they? So what multiple cores allow me to do is allows me to run two different programs at the same time. Okay, now we can code programs so they can use more than one processor. However, I have to be very clever in how I break my program up and how I do that, and that's known as multi-threading approach. And you know, that's definitely something that we have to plan ahead for, and not every program can do that. The next one is clock speed. This is how many instructions we run per second, i.e. the hertz. And this is how often we can run the FDE cycle. Okay, so the clock speed is how many times per second I can do the FDE cycle. Okay, so if I have a 1 gigahertz processor, that means that I have a clock speed of 1 gigahertz, means I can do 1 billion instructions per second. Okay, so that's what we refer to clock speed. A clock cycle is 1 FDE, okay, 1 fetch, decode, and execute. The last performance improvement that we can make is using cache memory. Now, cache memory is fast memory, so it has a higher transfer rate than normal RAM would be. So it can transfer data to and from the CPU a lot quicker than normal RAM can. Because of that, we can use it to store things we are currently using or frequently using. So anything which is being used a lot would be stored in cache. For example, let's say I'm editing a Word document. That Word document will be stored inside cache. But let's say I also have a PowerPoint which maybe I haven't touched for an hour. Well, that will be just in RAM. So cache memory will store things which are frequently being used, and it has a higher transfer rate. Because that faster transfer rate, it does cost a lot more memory. So cache memory will be a lot smaller in capacity, in the amount that it can store, than RAM would be. Okay.